Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today we'll discuss programmable logic controller interface methods. Our objective is to examine placement of emergency stop devices, auxiliary contacts, and overload elements inside variations of PLC-controlled systems, as well as discuss solutions to scenarios involving PLCs and field input and output devices operating at different levels of pilot voltage. This lecture is predicated on the assumption the viewer has watched the Introduction to PLCs lecture, available at the Big Bad Tech channel. If you haven't watched this lecture yet, or only dimly recall its contents, please take the time to do so now. Additionally, this lecture assumes the viewer has some general familiarity with 2- and 3-wire motor starter circuits as implemented using traditional hardwire relay-based ladder logic. For those necessitating review on this topic, you are encouraged to revisit the 2- and 3-wire control circuits lecture, available at the Big Bad Tech channel. A disclaimer before we begin. This lecture cannot, will not, and never makes the claim to replace due diligence on your part researching the specific interface mechanisms for your particular PLC or system of interest. Manufacturers offer numerous different, often incompatible interface methodologies, and the content herein can at most be considered general guidance in preparation to some specific application. Always consult the datasheet of interest for a particular system. You will recall that the fundamental operational principle of ladder logic is the establishment of two different levels of power: pilot and primary. Pilot or control signals are ordinarily low current, low voltage, low power signals that solely coordinate the action of interface elements like contactors and solenoid operated valves. Primary signals, in contrast, are high current, high voltage electrical or high flow, high pressure hydraulic or pneumatic input that does the actual work. When an interface element like a contactor or a solenoid operated valve is commanded to do so by a pilot signal, these interface components make or break connection to primary input. The separation and isolation of pilot and primary signals offer a degree of ease and safety for operators and technicians assigned to install, maintain, troubleshoot, upgrade, and repair electrically controlled systems. This concept should not be new to you, and if it is, I'm sending you all the way back to the beginning of the Electrically Controlled Systems playlist to begin anew. Look me up in 2 to 3 months when you get this concept down. Although this separation between pilot and primary signals should be simple in concept, complications to this methodology exist when we introduce a radically different means of control in the form of a programmable logic controller, or PLC. PLCs are industrial computers that, in summary, examine inputs, run a program, and issue outputs. PLCs, barring some peculiarities, closely mimic the behavior of those systems employing hardwired relay-based ladder logic. However, they are flexible, reprogrammable devices that make quick modification of a system possible without the time-consuming necessity of physically rewiring it. Two important complications exist when PLCs are introduced into the mix. 1. Does the PLC operate at the same level of pilot voltage as the interface elements like contactors and solenoid-operated valves? And 2. Can you trust a computer? Let's deal with the second issue I raised first, since it's of primary importance. I ask again, can you trust a computer, especially in an emergency? The answer is no. No, no, no. Not now, not ever. Never, ever trust a computer. When you surrender authority to a soulless and easily manipulated inanimate object, things can and will go wrong. The point being that pilot commands intended to initiate immediate specific action in emergency conditions should never originate from a PLC, but rather be physically hardwired into a system such that they can and will override a PLC. If there is one thing I learned from watching The Terminator, it is to never underestimate the duplicity and cunningness of an amoral program. This warning having been issued, a complicated system may necessitate involvement of the PLC to initiate an orderly shutdown. However, when it comes to those situations that count, never let a machine do your dirty work. When you need to kill it, and kill it dead, nothing beats a well-placed e-stop. For this reason, you'll often see PLC-controlled systems featuring e-stops wired in the following fashion. Consider a generic 4-input, 4-output PLC that operates on 120 volts AC. Let's first examine the PLC power input. A circuit breaker between the 120 volt AC source line connection and the PLC is for protection purposes and serves to completely depower the PLC-controlled system. Since this exercise has the potential to get confusing rather quickly, note I'm illustrating the line connection of the 120 volt AC source using a nauseating shade of purple, my second least favorite color, and the neutral connection of the 120 volt AC source using brown. Next, let's examine the input. Note the maintained contact normally closed e-stop is not a direct input to the PLC, but rather it serves as a hardwired bottleneck through which two field input devices immediately downstream of it must negotiate to issue input to the PLC. When the maintained contact normally closed e-stop is in the deactivated closed condition, the closure of any field input device will issue a logical 1 to the PLC. If, however, the e-stop is in the activated open condition, the closure of any field input device will not issue a logical 1 to the PLC despite repeated attempts to do so. Wired in this fashion, the hardwired e-stop directly above stream of all field input devices has effectively severed all incoming communication with the outside world without the necessity of resorting to any program to do so. Note as implemented, opening the e-stop would still keep the PLC powered up. The e-stop can also be configured as a direct input to the PLC by using another set of mechanically interlocked normally closed terminals. In this scenario, the top set of normally closed terminals still serves to sever communication with all those field input devices immediately below stream of it, and the bottom set of normally closed terminals acts as a direct field input to input 4. Used in this fashion, the e-stop still disables the field input devices, only this time the additional set of mechanically interlocked terminals allows the loss of voltage on input 4 to be used by the PLC program to initiate a specific program-based shutdown. It is for this reason the e-stop normally does not depower the PLC, but rather keeps it going to initiate the shutdown if desired. Let's now examine the output. Again, note the maintained contact normally closed e-stop serves as a hardwired bottleneck through which all field output devices also immediately downstream of it must negotiate to be energized. When the maintained contact normally closed e-stop is in the deactivated closed condition, the PLC can energize any field output device by closing the appropriate electromechanical relay. If, however, the e-stop is in the activated open condition, the PLC cannot energize any field output device despite repeated attempts to do so. Wired in this fashion, again, the hardwired e-stop directly above stream of all field output devices has effectively severed all outgoing communication from the PLC without the necessity of resorting to any program to do so. If the application warranted its inclusion, selective outputs can also maintain connection to the PLC regardless of the actuation state of the e-stop, perhaps to initiate the orderly shutdown of the system in an emergency or signal its occurrence. For example, the pilot lamp on the Q4 output is not disconnected from the 120 volt AC line connection via the e-stop. A very simple application of this selectively enabled or disabled outputs could be to light the fourth pilot lamp in the event someone triggers the e-stop. The inclusion of this single line in the PLC program would serve this purpose. A break instruction examining input 4 energizes and de-energizes output Q4. When the e-stop is in the deactivated closed condition, input 4 experiences a logical 1, and the break instruction examining input I4 does not permit logical continuity onto output Q4. Output Q4 is not energized, and the fourth pilot lamp is dark. Given this condition, the PLC is at liberty to direct the operation of this system with the rest of the program. If, however, the e-stop is in the activated open condition, most of the field input and output devices are disabled, input 4 and output 4 being the notable exceptions. In this condition, input I4 would experience a logical 0, and the break instruction examining input I4 does permit logical continuity onto output Q4. Output Q4 is energized, and the fourth pilot lamp turns on. When the e-stop is wired in this fashion, most of the inputs and outputs are still overridden. However, the selectively enabled input and outputs still allow the PLC to alert that an emergency stop condition has occurred. Various degrees of this technique could be used to initiate an orderly shutdown of a more complicated system. It should be stated that the placement of the e-stop is system and application specific and must take into account the needs of the process and those conditions that operators must be protected against. In summary, a properly placed e-stop should disable a system as quickly and reliably as possible with minimal, if any, reliance upon the PLC. In the interest of keeping things simple, let's just assume for this and the remaining applications that the e-stop is a hardwired bottleneck that disables all incoming and outgoing communications to and from the PLC. Before moving on with the rest of the contents of this lecture, Let me make a brief comment how interconnection with a PLC is represented schematically. Yes, I know I just walked you through a step-by-step tour of this system, holding your hand every step of the way, using easily identifiable colors. However, if someone threw this diagram on your desk, using only indistinguishable black and white, could you honestly interpret it with any sense of grace? I mean, look at this confusing nest of wires. I've seen more sense written on the side of a bottle of Dr. Bonner's Castile soap. Given time, you might be able to interpret this, but could your lab partner? No, they couldn't. They still have trouble differentiating between left and right. It is for this reason PLC interconnections are often illustrated using a dumbed-down form of ladder logic diagrams. Recall systems using traditional hardwire relay-based ladder logic simultaneously represent both interconnection and function using techniques as discussed in the ladder logic documentation lecture. However, since a PLC's principal advantage is its reprogrammable nature, one really only needs to schematically represent the hardwired connections. Very often, a PLC-controlled system represents this schematically as field inputs simply disappearing into the PLC and outputs selectively energizing or de-energizing the field outputs. However, gives no indication as to what opens or closes these outputs. Consider our present configuration illustrated far more efficiently in the following fashion. Here, the hardwired connection between the e-stop and the two downstream field input devices, the normally closed momentary contact red push button and the normally open momentary contact green push button, is made pretty explicit. However, the field signals kind of disappear down the rabbit hole of the appropriate PLC inputs. This is to imply an isolation between the field inputs and the PLC exists, and the PLC program assumes responsibility for all incoming transmissions from this point on. Additionally, the outputs can be more efficiently represented as the hardwired connection between the normally closed e-stop and the contacts of electromechanical relays Q1 through Q3, selectively energizing or de-energizing the loads attached to Q1 through 3. However, it remains unsaid what actually opens or closes the Q1 through 3 contacts. This is again meant to imply that the PLC program is in charge of opening and closing these contacts. All a technician needs to do is to wire the devices as indicated, and it's the program's responsibility from this point forward. Illustrated in this fashion, one can think of the schematic as only partially indicating functionality, but more to the point, how the system needs to be wired such that the PLC program can direct its operation. You might see subtle variations of this illustration method employed by different manufacturers. You'll note the power connections to the PLC are not expressly illustrated using this technique. Before moving on to the rest of the contents of this lecture, I recommend pausing it and comparing the two diagrams until you understand the direct one-to-one correspondence between the confusing pictorial and the far more compact schematic representation. For the purposes of this introductory lecture, I'm going to try and use both diagrams and take my time. However, expect me to eventually abandon the hand-holding and push you out of the nest to plummet to your death or soar among your equals.